So limit x tends to c, fx into gx also exists if limit of f and g exists and it is L1 into L2. Fourth, if L2 is non-zero. What is L2? What is L2?
Limit of
Limit
g
of
of
gx
x.
at c.
Right. Now, then, can I talk about limit of f upon g? Yes, because if limit of g at c is non-zero, then in some neighborhood of c, g is non-zero, and certainly fx upon gx makes sense in neighborhood of c. Right? Because fx upon gx as limit x tends to c, does it make sense? So x is away from c and x is tending towards c. So x is near c. And f of x upon gx makes sense provided gx is non-zero, and it is possible. We understand?
Yes,
Correct?
sir.
Okay, so now what is the proof? What is our claim? Given, what is given? Limit x tends to c, fx is equal to L1, and limit x tends to c, gx is equal to L2. Fine. So limit exists. So what is our first claim? Limit x tends to c, fx plus gx is L1 plus L2. So we can use sequential criteria. So f plus g is a new function, right? Let hx is equal to fx plus gx. This is a new function defined on same domain A. And we want to prove that limit of this function is L1 plus L2. So what is the sequential criteria? So let xn be a sequence of numbers in A, right, in the domain, such that limit n tends to infinity xn is C. So I have chosen a sequence in a domain which converges to C, because we already proved that. See, let me note here. Note. So limit x tends to c, f of x is equal to L if and only if. What we have proved? For any sequence xn which converges to C, the sequence fxn converges to what? Fxn converges to L, right?
But sir, how can we prove that limit of x tends to c, f of x is equal to L? Because one sequence is not enough.
Limit of function at C is L if and only if you choose a sequence in domain which converges to C, the f of xn converges to L. This theorem we have already discussed.
Yes, sir.
Right. So whatever sequence you select, if it this is your domain, and you choose any sequence xn converges to C, at the same time, if this is a graph of function and this is L, at the same time f of xn converges to L in the codomain. This is equivalent. Every sequence. No, this should not fail for any single sequence. Right? So what is your question?
No, sir, it got cleared.
Okay. Now, so since this is if and only if, that means if you choose, just close your eyes and choose a sequence which converges to C, and if it happens that key f of xn converges to L, then we can declare that L is a limit, because this is true for every sequence. It is not, it doesn't fail for any sequence. If so, then we can declare it, but if it fails for single sequence, then we cannot say L is a limit. Right. Okay, so this is equivalent to say that L is a limit, and therefore if you want to prove that limit of hx is L1 plus L2, then what is the equivalent criteria? If you want to prove that limit of, see, what is our claim? What is our claim here? Limit x tends to c hx is L1 plus L2. This is our claim. And if you want to prove that your claim is true, the sequential criteria says that you choose any sequence, arbitrary. If it converges to C, prove that hxn converges to L1 plus L2. So do we agree what I am saying?
Yes, sir.
Yes, sir.
So this is a logic. Now I have chosen, I just close my eyes and I just select arbitrary sequence which converges to C, not any specific or special sequence. It converges to C. What is my claim? What I expect? We expect that, what we expect? What we expect? What we expect is equal to what?
L1 plus L2.
L1 plus L2. This is our claim. Let us try to do this. So since limit of xn is equal to C and limit x tends to C fx is equal to L1, limit x tends to C gx is equal to L2, what we have by sequential criteria, what is limit n tends to infinity fxn? What is it?
L1.
L1. Very good. So, because f limit of f is L at C and xn converges to C, by sequential criteria this must be L1 because limit exists. And what is limit n tends to infinity gxn? What is this?
L2.
L2, right? Do you understand it clearly? There is no confusion at all. It is very straightforward. Therefore, what is limit n tends to infinity hx is limit n tends to infinity fx plus gx, limit n tends to infinity x hxn is equal to limit of fxn, limit of gxn. Now we are approaching along the sequence, but what is inside the bracket? Sum of two sequences, because fxn is a sequence, gxn is a sequence, and sum of two sequences. What is the limit of sum of two sequences? Is it sum of limits of sequences?
Yes, sir.
Right, I am using the results from sequences, not anything else. So fxn is a sequence, gxn is a sequence, and it is limit of sum is sum of limits. But what is the limit of fxn is L1, limit of gxn is L2. So what is the conclusion? For any sequence xn that converges to see the sequence fxn plus gxn converges to what? L1 plus L2. Therefore, by sequential criteria, of limit by sequential criteria of limit. For every sequence this is going to happen by sequential criteria of limit x tends to c fx plus gx. What should be? L1 plus L2. That means limit x tends to c of fx plus limit x tends to c of gx. Fine. Logically everything is clear.
Yes, sir.
Right, and therefore basic proof for sequences we did in the last semester, calculus 1. That basic proof was कि given epsilon we could produce k and so on. But that result we directly accept here because we have some one result sequential criteria. So similarly, limit x tends to c fx minus gx is L1 minus L2. Similarly, this can be proved. Now let alpha is a real number. So what is our second claim? What is our second claim? Limit x tends to c alpha times fx is equal to alpha times L1. That means alpha times limit of fx as x tends to c. This is what we want. Fine. By sequential criteria, what we expect? By sequential criteria, what we should prove? Because sequential criteria makes our job easy. Right? Yes. What we expect? Let hx is equal to alpha times fx. Suppose this is my function. So what we wish, what we want to prove? Limit x tends to c hx is alpha times L1. This is what we want. But when we want to prove that limit at x tends to c hx is some number alpha times L1, by sequential criteria it is equivalent to proving that.
For all sequences xn, the limit xn n tends to infinity is equal to c. Limit of hxn is equal to alpha times L1.
Right. Therefore, if you choose any sequence, so choose sequence now. Let xn be any sequence, any, not specific, that converges to C, converges to C. That is any sequence in domain. Basically, it makes sense if xn is in domain, then only you can talk about fxn. That is, xn belongs to A for all n, and limit of xn is equal to C. So what we claim? So limit of hxn is alpha times L. This is what we want. Okay, let us consider. So limit n tends to infinity hxn. So limit n tends to infinity alpha times fxn. Hx is alpha times fx. Right? Now this is limit of sequence. And use the direct property of limit of sequence. What is limit of alpha times yn for sequences? What is the limit of alpha times yn? Alpha times limit of,
Alpha into limit of y.
right, alpha times limit of yn. That we know. If you multiply by scalar to the sequence and if you evaluate limit, it is alpha times limit of yn. We can shift the limit towards yn. So, and fxn is a sequence like yn and it's multiplied by scalar. So, what is it? Alpha times limit of fxn. But limit of f is L1, limit of f is L1. Therefore, what is the limit of fxn? Since limit of f at c exists and xn converges to c, so what is this? L1, right? Therefore, limit x tends to c, alpha times fx is alpha times L1, because for any sequence this is going to happen. Third one, what we want? So limit of fx into gx is L1 into L2. This is what we want. So what is the strategy? Let xn be a sequence in A such that limit of xn is c. Choose a sequence converging to c. Then what is limit n tends to infinity fxn into gxn? This new product function and apply it on xn. So this is sequence now. And what is the limit of this sequence? It is a product of two sequences, right? It is limit of product, and is limit of product is product of limits, is limit of gxn. I am using the results from sequences, right? And what is the bridge to connect these two things? What is the bridge to connect these two things? The result for sequences and results for limit. Sequential criteria.
Sequential
Right?
criteria.
So limit of fxn is L1 and limit of gxn is L2. Right? Thus can we declare that limit x tends to c fx into gx is L1 into L2, because for any sequence this is going to happen. So we can declare by sequential criteria limit is this. Similarly, you prove that limit x tends to c fx upon gx is L1 upon L2. So similarly, you should try to prove this. And because of this theorem or algebra of limit, you can evaluate limits of some functions easily, which you were using in 12th standard. What is limit x tends to 1 x square plus 1 upon 5x minus 3. So what is this limit? Yes, it is limit x tends to 1 x square plus 1 upon limit of 5x minus 3 as x tends to 1. The limit of quotient is quotient of limit. So this property we are now adopting here. And what is the limit of numerator as x tends to 1? That we can understand directly, that it is 2 upon what?
2.
Which is 1. That, so how, so this makes easy. Now this becomes simple because now we have the above theorem, right? So if fx is equal to constant function, right, then what is limit x tends to a fx? What is the limit of constant function?
Constant.
Well,
Constant.
same number, right? Now if fx is equal to x, then what is limit x tends to a fx is this? We have already proved this. What is it? Yes. Is it a?
A.
Right. Now if fx is equal to some a1 times x, then what is limit x tends to a fx a1 times a, correct? Now if fx is equal to x square, and what is the reason? It is a1 times a by previous theorem. It is limit of a1. A1 is a constant, so limit a1 into limit of x. Limit of x is a. That therefore it is a1 times a. So limit x tends to a x square is a square. This also we have discussed. Now, if fx is equal to x to the power n is positive integer, then what is limit x tends to a x to the power n? What we expect? What it should be?
A raised to
A raised to n. So prove this. We have proved up to 2, 3, but you try to prove it by induction for any positive power n. Right? You should work it out. So what is the my point? So if fx is equal to a0 plus a1x plus a2x square plus an x to the power n. What are a1, a0, a1, an are constants and n is positive integer. N is some positive integer. This is my function. So is it a function?
yes,
Is
sir.
it a so this is defined on R. Now my question is, what is limit x tends to a fx? Use the previous theorem. Idea is use the previous theorem. What is it? Plus what is the limit? Now it is just addition of some functions, and therefore what is it? Limit of a naught plus limit of a1x plus limit of a2x square and so on. We can distribute this limit inside the bracket and then use the multiplication with scalar. So ultimately what is it?
A a naught plus a1 a plus a2 a square. Dot.
Just replace a by x by a, and so can I say that it is f of a? F evaluated at a, correct?
Yes.
Yes,
Yes,
sir.
Right.
sir.
And therefore, for polynomial, limit at any point exists and it is value of that polynomial at that point. That is what we can see from this easily. Right? Fine. Okay, so suppose f is defined on 1 to 2 to r, and f of x is equal to uh, x square, then what is limit of f at 1? What is limit of f at 2? Right? What is the limit of f at 1? What is limit of f at 2? So when my domain is 1 to 2, That means left side of the 1 is not in our domain and right side of 2 is not in the domain. Whatever is between 1 and 2. So this is the universe for this function. So in this case, limit x tends to 1 fx is actually limit x tends to 1 from right side only, right? And limit x tends to 2 fx is nothing but limit x tends to 2 from left side, right? We can approach only from left side towards 2. Right side is not, is right hand side of 2 is a vacuum, we cannot approach, right? And therefore right hand limit and left hand limit. So what is a right hand limit? Suppose f is defined on a belongs to R is a cluster point of domain of function, then a number L is said to be right hand limit of f at a if. Now how will you make the definition of right hand limit? So this is my a and I am approaching towards a from right side. So left side is not at all considered in this case, right? At present x is here. So what definition or how to make the definition in terms of our basic in the same view of our basic definition of it. If given any epsilon there exists delta such that what? Such that
X minus a is less than delta implies mod of f of x is minus l is less than
so x
epsilon.
minus is less than delta, but it means that x belongs to a minor delta and a plus delta. But we are not sure about left hand side, or we don't want to consider left side a minor delta to a. We are not interested. We are just
No, sir, only if only x minus a we consider.
okay. But when I say x minus a is less than delta, then it may happen that x minus a is negative. That means x is less than a. That may be possible. Negative numbers are less than delta. So which part of
0 less
neighborhood
than x minus a.
so which part of neighborhood I am interested in? So a to a plus delta. I am not interested in a minor delta 2. Do you understand? We are not interested in this part and we are interested in this part. So for every epsilon there exists delta. So same definition, only we are interested in right hand side. So such that x belongs to a plus delta implies distance between fx and L is less than h. So is it clear? Yes.
Yes, sir.
Right. And
Yes,
so
sir.
this doesn't,
Yes.
so with respect to this expression, there is no confusion at all because x is not equal to a. So x is greater than and less than a plus delta. So for these values of x, the distance between fx and L is less than. So right hand limit is denoted by limit x tends to a plus fx is equal to L, Wait, so what does it mean? Ki limit extends to a plus fx means approaching from right hand side, and it is equivalent to this. Thus, limit extends to a plus fx is equal to L if and only if. What is the equivalent to saying this? Given epsilon, there exists delta, so such that 0 less than a less than x less than a plus delta implies distance between fx and L is less than epsilon. Right. In this way we can define the right hand limit. Similarly, how to define left hand limit? So left hand limit. So let f is defined on A to R. A belongs to R is a cluster point of a real number L is said to be the left hand limit of f at A if. Now, analogous to the previous definition, can you tell me what should be the definition for left hand limit? We are approaching from left side now. If
For any given epsilon, there exists delta such that x belonging to a minus delta to a implies that mod of f of x minus L is less than epsilon.
a minus delta to a, right? X belongs to a minus delta to a. Then distance between fx and L is less than epsilon. Right. So if this happens for every epsilon, can we produce delta? So then it exists. So left hand limit of f at A is denoted by limit extends to A minus fx. So limit extends to A minus fx is equal to L. Right. Now theorem, which is important theorem which you were using in 12th standard directly. What is the theorem? So let A subset of R, A belongs to R, is a cluster point of A and f is function defined on A. A real number L is limit of f at A if and only if. Now this is if and only if. What is if and only if? Limit extends to A plus fx, limit extends to A minus fx exists, and so L is a limit of function f at A exists, and limit extends to A plus fx is equal to limit extends to A minus fx is equal to L. That is, Alternatively, limit x tends to a fx is equal to L if and only if limit x tends to a plus fx is L and limit x tends to a minus fx is also L. So when we declare that L is a limit, if right hand limit and left hand limits are equal, right? And so what does it mean? If right hand limit and left hand limits are not equal, then L is not limit or limit of function does not exist. This is what the result we were already using, but this is true. Okay, so how to write the proof of this? Yes, so we'll try to write some part of proof. The rest of the part you can complete because the ideas are similar. We are playing with same thing again and again. For epsilon, try to produce delta and so on. Right, so we are playing same game, epsilon delta game again and again, and so now you should be comfortable so that okay, so suppose limit x tends to a fx exists and it is L, right? So what is our claim? What is our claim? Yes. What is our claim? Right hand limit is also right hand limit exists, left hand limit exists, and they are same as L. This is our claim. But by definition of right hand limit or left hand limit, how to start the process? How will you prove that right hand limit is L? Given that limit is L, given
Given
that
absolute literally zero.
correct by definition. So we claim that okay, let me write claim clearly. So given epsilon, there exists delta such that if x is in a to a plus delta, x is in a to a plus delta, then f of x minus L is less than epsilon. If you prove this, then we say that for every epsilon we can produce delta, then right hand limit is L. So start with epsilon. Given epsilon, want delta. Okay, so how to produce delta? Yes, how to produce delta? What is the given data, given information? Right?
Yes, sir.
So limit of function at a exists and it is L. It is given. How to make use of this? Given epsilon, since limit x tends to a fx exists and it is L by definition of limit, what should I say further? What should I
There
say?
exists a delta such
There
that
exists delta such that whenever x is in a minor delta to a plus delta, x is not equal to a probably, we have distance between fx and L is less than epsilon. So by definition of limit, given epsilon, whenever a minor delta and here a plus delta, For every x in this range, f of x minus L is less than epsilon. Now, can I say that ki x belongs to a plus delta, then fx minus L is less than epsilon? Can I say this?
Yes, sir.
Yes, sir.
Right, because it is actually part of this big interval a minor delta to a plus delta. So for small part, half part, certainly it is true. This is what we wish to prove. We claim that given epsilon there exists delta whenever x is in this neighborhood. We have this. So this is true, right? Hence, for any epsilon, there exists delta. Certainly, we can produce delta such that x belongs to a plus delta implies distance between fx and L is less than epsilon. Similarly, for epsilon, there exists delta such that okay. So hence, can I say that right hand limit at a is L, right? Similarly, given epsilon, there exists delta such that whenever x is in a minor delta to delta a minor delta to a, what we have fx minus L is less than epsilon. Same idea, because since limit of function at a exists and it is L, so there exists delta. Then choose this part of neighborhood. It is true, right? Therefore, limit x tends to a minus fx is L. Thus, limit x tends to a minus fx is limit x tends to a plus fx is L. Fine. So half part is done. How to do the next half part? So converse. What is a converse? What is a converse?
If left hand side limit, right hand side limit are equal to L, then limit exists.
Right. Right hand limit and left hand limit is same. Then we claim that. So limit x tends to a fx is also L. Exists basically. And so what is a natural way from our knowledge so far? How to prove that limit is L? What is the natural way?
For given epsilon, we produce delta.
Right, given epsilon. Because our claim is this, remember. And to prove this, we given epsilon, can we produce delta? What we want? Delta. Such that whenever distance of x from a is less than delta, right, then fx minus L is less than epsilon. That is, x belongs to a minor delta to a plus delta, x may not be a, then distance of fx from L is less than epsilon. So this is what our aim. Epsilon is given. What is in my mind? Whatever going on in my mind, I have written it in bracket. I want delta. Okay, so how to start the process? What is the assumption? What is the assumption? Right hand limit is L, left hand limit is L. So since right hand limit is L, so for this epsilon, what happens? For above epsilon, by definition of right hand limit,
There exists a delta 1.
there exists delta such that whenever x belongs to a plus delta 1, then certainly fx minus L is less than epsilon. Right. Now, also limit x tends to a, left hand limit of fx is also L for same epsilon. By definition of left hand limit, there exists another number delta 2, may not be same as delta 1, such that x belongs to a minus delta 2 to a, we have fx minus L is less than epsilon. Okay, now what is the current situation? What is the current situation? A plus delta 1, and what is here? A minus delta 2. So what is this distance on left side? It is delta 2. What is this distance on right side? Delta 1. Do you understand? These two distances may not be same. Okay, let me make picture more clear. So this is a plus delta 1, and this distance is delta 1. These two distances may not be same, but in which neighborhood fx minus L is less than epsilon? Either it is on right side or left side. In which neighborhood?
Minimum of delta 1 and delta 2.
Right, because if x is on right side up to delta a plus delta, fx minus L is less than epsilon. If x is on left side up to a minus delta 2, it is less than. Right, so therefore what is the minimum? If delta 2 is smaller than delta 1, then you choose minimum. In that range, both things are true. Either a point is on right side or left side, doesn't matter. Right, so let delta is equal to minimum of whichever is minimum, choose that as a delta. Then if distance of x from a is less than delta, or that is x belongs to a minus delta to a plus delta, x is not equal to a, or x belongs to a minus delta to a union a to a plus delta, then what will happen? If x is on left hand side a minus delta to a, can I say that f of x minus L is less than epsilon? Either x is here or x is here. In union anywhere, no problem, it is less than epsilon. Right? What is the conclusion? What is the conclusion? Given epsilon, there exists, we can produce delta such that whenever distance of x from a is less than delta, doesn't matter it is on right side or left side, the certainly distance between fx and L is less than epsilon. And this is true for any epsilon. Hence, can we declare limit x tends to c, fx is equal to L? Correct? Point. Let find. Okay, so does limit x tends to 0 fx exist? Does this limit exist? My function is f of x is equal to absolute value of x. Right? Does limit of this function exist?
Yes, sir.
Can you sketch the graph of this function?
Yes, sir.
It is same as x if x is positive. Right? If x is positive, absolute value is x. It is minus x if x is negative, and 0 if x is equal to 0. Correct? And what is the graph? Can you sketch the graph? Okay, let us think about positive part. On positive side, it is just y is equal to x. F of x is equal to x. Like this on positive side. On negative side, it is like f of x is equal to minus x. That means y is equal to minus x. y is equal to minus x, and y is equal to x, and 0 it is 0. So this is a graph. Do you understand? Is it correct?
Yes, sir.
Yes, sir.
Now what is limit of this function? So limit x tends to 0 from right side. First we approach from right side. So we are approaching to 0 from right side means x is on the right side of 0, fx. So limit x tends to 0. Now we are approaching from right side, but on right side what is the function? X approaches to 0 from right side. At present x is on the right side, and therefore for such x, what is f of x? What is f of x? X, because at present x is on the right side, and on right side f of x is x. And what is the limit as x tends to 0 of x?
0.
0, right? Irrespective of any other confusion, it is as x tends to 0, x is 0. Similarly, okay, again you can think about this, but it is true. So what is limit if we approach from left side, right? So limit x tends to 0 from left side. When we approach from left side, at present we are on left side of 0. At this x, what is f of x?
Minus
Minus.
x.
minus x.
Minus x. But then we know that minus x is minus 1 times x, right? So minus 1 into limit x tends to 0 of x. And what is this limit?
0.
0. Therefore, what is the conclusion? Limit x tends to 0 from right side is same as limit x tends to 0 from left side, and it is 0. And by previous theorem, can we conclude what is the limit of fx at 0? Is 0. Correct?
Yes.
Yes.
Now, so let f is a function defined on R to R. What function I am defining? F of x is equal to absolute value of, okay, uh, I am defining this function for non-zero numbers. I want to define this for uh, r minus 0. I don't want to define it at 0. Right, f of x is equal to absolute value of x upon x. Is it a well defined? Is it defined every element of domain? Yes.
Yes, sir.
Right, because problem could be at 0, but 0 is not in the domain. We have excluded 0. Right. Now, does limit x tends to 0? Can we talk about limit at 0?
It does not exist.
No.
We can talk about limit because 0 is a cluster point of the domain, but exist or does not exist, that you think about. Right? So, note that, can you sketch the graph of this function?
Yes, sir.
Right? If x is positive, absolute value of x is x, therefore it is x upon x1. And if x is negative, what is absolute value of x?
Minus 1.
And therefore it is
Minus
minus
x.
x upon x, so minus 1. And therefore if you sketch the graph of this function, if you sketch the graph of this function, for positive x it is 1, and for negative values it is minus 1. So for positive side it is constant, for negative side also constant, but values are not same. And therefore if we approach from right side, right, if x is here and if we approach to 0, what happens? The point value will approach towards 1. And if we approach from left side, then value will approach to -1. So right hand limit is 1, left hand limit is -1. You check this. So not same, so limit does not exist. So this function is called as a signum function. Signum means what? Or HGN, sign of x, right, is fx. And what is the sign of x? Is 1 if x is positive and -1 if x is negative. So this is just the name signum means sign of function. So signum function, sign of x. 1 means positive, -1 means negative. So that is the just name, otherwise nothing else. Right? So everything is clear.
Yes.
Yes, sir.
Now this is just exercise. Evaluate. Limit x tends to 0, 3x square plus absolute value of x upon absolute value of x minus 1. Evaluate limit at x tends to 0 of this function. Okay, so we'll stop here. If you have any doubt, you can ask. So tomorrow we will have practical session at what time? 11, right?